thanks for having me. First of all, if you want to ask any questions, if anything comes up, please ask them on Slido. I'm asking this question, what can we do, what do we need to do to continue advancing deep learning? Because the last 6 years have been amazing. We've made a huge progress coming out of playing super simple video games to playing very complex ones, and we just expect things to continue. But how? There are certain limits. Why has growth happened? Do we need to change something? Those are the questions I want to ask today. And I should say I started working on deep learning around when this hype started. So I got into it at the perfect time you could potentially get into it. And back then, we didn't know how it's going to turn out. No one really knew. Now, no one knew how much contribution to AI success is going to be due to algorithms and how much is going to be due to compute. And we've learned a lot over this last 6 years. What I want to do with this talk is I want to tell you a little bit about the history, not the 60-year history, but rather the 6-year history of deep learning research and what drove it, what the shortcomings are, what the definite and clear upsides and wins are, and then think about what we need to ask ourselves to find ways to continue. But first, the reason why I got into machine learning in the first place is because back then I thought, well, if we can get human-level AI, it can probably solve problems for us that we can't solve. It turns out that that's largely untrue. We have lots of very good AI, but it's still not that intelligent. So I turned to other things. As you see, I now work /founded a company called Climate Science. We are a team of 15 people building an educational app for schools to learn about how to actually fix big problems, because apparently AI can't do it for us yet. So disappointed in that, but finding other ways to do it. Let's get to it. First, I want you to think about AI not just as a technology, but as a science. Science starts somewhere where we know nothing, and then we learn something. I like to take Newton's law of gravity as an example here. It works. We look at the sun, we look at our neighboring planets, and we think it works. Makes sense. They pull each other. It's about right, but it's not quite right. And we didn't know why for quite a long time, until we came up with the next theory, Einstein, theory of relativity. And more stuff happened. This theory, Einstein's theory, predicted black holes, and after some time, we actually managed to take an image of it. This image of a black hole, the first image ever taken, is one of the best examples of science trying things, coming up with new ideas, and at some point arriving, proving that it was right in what it said. Well, we aren't there yet with AI, but we're getting closer. Let's think about AI as trying to solve this problem, the problem that we are all solving. The only thing we give the universe are muscle movements. That's something I often say, because it's true. I can't speak. I can move muscles that then move my vocal cords and breathe out, and we call that speaking. I can't move my arms. It's just muscle movement. So that's our output format. We have a similar input format. We see, we smell, we feel, and we get feedback. Do we live or die? That's evolution, just telling us if we're performing well in the world we're living in. We construct our own values and give ourselves feedback, but this is really how we interact with the universe. We've tried to build this with AI too. Call it reinforcement learning. That's why I work on it, because I think it's most closely related to sort of the most sensible way of learning. An agent gives an action to an environment. It gets back an observation. Say, playing a video game, you get the screen, and you get back a reward, which is like living or dying in the universe. The idea is pretty simple. We want to play, and while we play, we want to choose our actions such that we maximize our reward. Right? We want to do the things to survive. We want to do the things to win at whatever we want to win at. And through examples, through experience, we learn. That's the idea of reinforcement learning, and learning in general, really. There are many ways of doing this, and a couple years ago, 6 years ago, this was exciting. An AI playing a very, very simple Atari game from pixels. It was a Nature paper published by DeepMind, major research finding. Well, around now, we're playing these kind of games with AI.
And the flat cannon.
He was not ready there. And that's all it took. A couple.
What you see here is a 5v5 game. So 5 independent players against 5 independent players.
He's getting chased. He's getting dove. The chain frost being bounced between them perfectly.
And that's AI beating up the pros. Best human team in the world. Group of 5 have to coordinate, being beaten by AI. I think the complexity level from like this to that, pretty big jump for a few years. So why? Of course, there are some obvious answers, more compute, right? But are there ways to continue advancing at this pace? And if so, how? Let's look at a few more examples of what AI does and how it does it. So maybe we can ask the right questions we need to ask to find ways to continue. So this is still reinforcement learning, but there are other ways, more complex ways of interaction between agents. I like to give an example it's called generative adversarial networks. Some of you might have heard that term. I like to describe them with George the generator and Donald the discriminator. What you get is these two are friends from childhood. That's the story I always tell. George was never really good at much, so he just became a criminal, but he always wanted to be an artist. And Donald the discriminator, just, the correct guy, but he likes helping his friends. So what they decide one day is Donald is going to help George become an artist. But George, being the person he is just going to try to fake pictures, fake draw images from a famous artist. So what happens is this feedback loop comes to life. George draws something that, doesn't look that great. Donald gets some real pictures, some real images from real artists, and George shows him his pictures too, and, Donald tries to tell them apart. And the idea is if Donald can't tell them apart, George paints like an artist, right? That's where we want to get to. So that's the feedback loop they play in. George becomes better at generating fake images, while Donald becomes better at discriminating, or differentiating, in other words, between fake and real images. And if you continue this for long enough, and I'm skipping some details here, but the basic idea is that, then you get George being a good painter. Now, if we replace these cute figures with neural networks, and then the first painting won't look that cute, but the idea is the same. It works. You train these two networks sort of against each other, and what it converges to in many cases is that the generating network generates real things. And again, so it would work. A famous result that comes from this kind of technique is this fake speech by Obama. The video and the voice is fake.
For instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now,
not his words.
You see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous
So we could dive into the, privacy and danger sides of this. This is not what this talk is about. It's more about the fact that this is possible and that's amazing. And we want to see how we got there and how we can continue similar things and the ideas of generally having AI create things. One more example I want to give of AI before we ask the important questions. I like to do this game with audiences. Please predict the next word that this is going to be a sentence, right? The machine is the first word. Try to predict the next one. Just scream it out. Good. I started easy on you. Machine learning algorithms build a mathematical off sample known as training data in. Yeah, that's where people usually go quiet. Okay, in order to make, let's try. Sorry? Conclusions, predictions, right. So, okay, this is getting to the exact point I want to get to. It's predictions or decisions without being explicitly blah, 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 continuing. The idea is you have to understand two things to do this. You have to speak the language, okay, that one's quite obvious. And you have to understand what you're speaking about. How would you know that it's machine learning? Okay, there's a talk about machine learning, that one's easy. How would you know that it's a mathematical model? Well, you must know something about machine learning to know that. And the further we get, the more complex we get, the more you have to know. And the thing with in order to, that's just language and sort of guessing how likely each possible word would be next, which is learning language. So what researchers have thought they could do is feed tons and tons of text about any subject to an AI and let it do that. Let it predict the next word on all of this text over and over again, and then the AI will learn something about that data set and the information contained within it. I guess that makes sense, right? Because in order to predict the next word, we have to understand what we're talking about. And if we train a neural network on predicting the next word and it gets better and better, it must get better at understanding what it's doing. And yes, this works. And it's been scaled up hugely recently and turns out to be very, very, very effective. So you use a huge neural network with 1.5 billion parameters. That is neural network weights. Sort of for reference, that's a good 1,000 times bigger than what you might run at home, if you run a decently big one. Well, medium. it worked very well. They trained it on Reddit. Most of you probably know Reddit. They trained it on links from Reddit. What they did is, and this is work by OpenAI, by the way, they crawled Reddit for all links that on posts that have some level of upvotes that they wanted to see, and then they clicked the links, and whatever the content was, they took that. So what they tried to get to is have a super diverse distribution of content, basically. Because you'd say if there's a link on Reddit, no matter which subreddit, pointing to something, it will talk about something. And if the post is upvoted a lot, then probably the content of this link is going to be good, no matter in which direction. So what you get is a very, very big, very high quality, very diverse data set. This turned out to be very important. Take this. This is generated by an AI. And I'm going to get to what we need to do to continue getting advances like this. But we first need to understand what we have. We have this input text. This is how we start with. Let's read this. In a shocking finding, scientists discover a herd of unicorns living in a remote, previously unexplored valley, the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And now we let this neural network that we trained on tons and tons of text continue our story. Let's see what it wrote. The scientists named the population after their distinct horn of its unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. George Perez, the AI even gave the scientist a name it didn't have before. An evolutionary biologist from the University of La Paz. I didn't Google whether it exists, but it might. And several, you see where I'm going. This is good. They had 10 attempts for this, so they generated 10 possible continuations and picked the best one. So this is after 10 trials. But the idea is clear. AI can write. We give it some idea of what a story should be about, and then it's going to write something. And if we don't like it, we just press again, and it's going to generate something new. That's what they did 10 times. Okay, that's nice. Good creative tool. Actually, pretty good creative tool. But it can do much more than that. If we feed it something like this, the same model trained on this huge amount of Reddit data, we feed it something of this form. We have an English sentence, say, I like cats. And then I translate that to French. Now, I don't speak French, but if I did, I could tell you what that means in French. And we have some separator token, another sentence, say, I am standing on this stage and giving a talk. Could translate that to French and put it in there. We do this a couple times, and we feed this as sort of the beginning of the story. Then we give it another English sentence and an equal sign. You know what it will do? It will translate that English sentence for you. It wasn't trained on translation. It doesn't even know what translation means in that sense. But it's just like, yeah, given this beginning of a story, it makes sense for me to translate this. It probably saw some French content, so it speaks some level of French. And then it just does it. We never told it what translation means. And we never told it that we wanted to do translation. We just gave it this input. This is what we call task transfer. So we train an AI on one task, and then we use it for another. Something very, very, very important in AI. When people talk about general AI, what they want is something that we train here, and then we use it everywhere. That's somewhat of a start, if you think about it. We trained it on something, and then now we can use it for other things too, that it really doesn't know about, or at least it shouldn't, from where. Right? And one thing that's very important from this chart, it's pretty trivial, like once you know it, if you keep scaling up your neural network, i.e. have more parameters, more neural network weights, it will get better at these transfer tasks. So same data set, but bigger neural network will do better on transferring if the data set is good. Okay, time to ask the important questions. Why? Why did we make these advances over just 6 years? How the hell did it go from we're excited of it playing a super simple video game to it translating when we're not even asking for it directly, playing 5v5 real-time strategy games? How the hell did that happen? And what do we have to do to continue this? So 3 open questions that I see for the future of AI are the following. Is compressing data equivalent to understanding? If you think about neural networks, what are they really? They are a data structure of some size that we change in order to map from some inputs to some outputs. Think about it. We give it a sentence, we want another sentence out. We give it an image, we want to know what's in it. So we're mapping something to something. And this neural network in the middle is trained, or people call it training, you can call it whatever you want, is trained to understand the relation between the inputs and outputs, which essentially, if you have a data set, that contains examples of this is nothing but data compression. Neural networks are a data compression algorithm that turns out to be a good generator for new data as well. Is that equivalent to understanding what we humans call understanding something? That's an interesting question. Neural networks are very, first guess. You give them something, they give you something, and they don't think about it, if you know what I mean. They're not going to sit there for 3 minutes and reason. They're just going to give you their decision, and then they call it a day. There's just a big problem of explainability, I guess. There are some works on how to make them more rational and more sort of reasoning-like. That's an interesting direction, I think. That's one we should probably explore more, sort of combining these two sides. And then the last thing that unfortunately hasn't been closed by the AI research community yet is a truly general purpose algorithm, one that can do all these things without us tuning all the details. What's the answer? I think we should stop scaling data and stop scaling compute. And luckily, the universe forces us to do that anyway now. And we should start scaling thinking. And I'll tell you more about what I mean by that in the next few slides. This is a chart of compute power used in AI. You see this DQN? That's the paper I showed you that played these Atari games. This very simple game, just the pixels. You see Dota 1v1? That's where they played this super big game, this complex game, with just 1 versus 1. The new one, where they played it with 5 versus 5, is way off. It's not even on that graph, actually, because I don't know why it's not on it, but it's way above that. AlphaGo Zero, DeepMind's work that played Go, look at this. This is a log scale. I mean, this is obviously important. It's just huge how much more compute we've used. So yes, we're playing more complex games. Yes, we're beating professionals at them. But, yeah, we're using 1 million times more compute. That's not very surprising, I guess. Is that sustainable? Well, not really, I guess. Even at some point, Google servers are over. Okay, maybe we can 10x it again. 1 more of these squares on the top. Can we 10x it again and again and again? I don't think so. And even with this scale, the number of neurons in artificial neural networks is tiny compared to our brain, even at that scale. So clearly, compute scale is not going to do it unless someone comes up with a way to do quantum computing with AI like tomorrow, but we'll see. Let's see, is there another way of doing it? Maybe a more efficient one? Turns out, yes. The research field I'm involved in, which works on imperfect information games, solving games where you don't know everything, the most complex class of games, if you will, recently had a paper published by one of my colleagues, Pluribus, a paper where they played 6-player poker. So an agent was placed against 5 professional poker players, and in each seat, so the evaluation was fair, and they played hands and saw who won. So far, it wasn't very much a thing to beat professional humans at 6-player poker. It was only very recently achieved to beat one at 2-player poker, and that required insane amounts of compute too. It turned out he did 6-player poker for $150 worth of compute. Not kidding. One of the games that was unsolved before, the first solution that comes up for it, $150 worth of computing power. One of the most complex games, we thought, hard to solve. None of the algorithms we had so far could solve it. Not even the ones that take 10 million times the amount of compute could have done it. But his algorithm did it. Why? Well, that's the trade-off, and that's the first important question we have to look at. His algorithm didn't use neural networks at all. It was purely based on tree searching and computing values explicitly, some clever abstraction tricks that are only applicable to the game that they were deployed in. So what they did, they just used the heuristic method. If you want to do things like playing super, super complicated games that we can't really properly, just describe with numbers, we kind of need all the complex information related to it, and it's hard to abstract them. What we'd need to do is we'd need to be able to allow agents to understand and predict their environment. What do I mean by that? Well, so the reason why this Dota agent needed so much compute is because it needed so much experience. It just played Dota a lot, basically. If we can make it play Dota less and optimize the way that neural networks are run, we could gain some performance improvements. Think about how you solve problems. When you play chess, you don't have to simulate 1 million runouts. You just think about what's going to happen. And you don't explicitly move the chess pieces, you think about it, and maybe you apply some intuition, but mainly you think about it if you're a good chess player. Similar stuff is true for Dota and other games. And if we can train AI to do these environment predictions well, we might get around the need for simulating unbelievably insane amounts of compute. Thousands of years here in experience for Dota is not equivalent to thousands of years of human lifetime, but thousands of years of always playing. And that's a little more than a human ever had. The second point is generality of observation. If we train an AI on one context, and I think GPT-2, this OpenAI work, it received a lot of criticism, but I think it shows this point very well. If we train AI on the information we have out there, on all of it, with all the complexity and all the unstructuredness, it learns more. If we train an AI to play tic-tac-go, how the hell should it know what a tree is? How the hell should it know what Dota even means or play it? So we need to train AI on tasks that are as complex as the ones we wanted to finally solve. And they need to sort of incorporate the exact type of complexity that we care about eventually. We humans are trained on life. That is our training task and our evaluation task. Intelligence is defined, at least by a big part of the AI community, as performing well within your domain. If we define our domain to be complex and broad enough, that's all right. So that part, well, we just need to train on a lot of things, the same agent on a lot of things at once. A good example of why this is failing so far is a recent publication, again by OpenAI, who looked into this. They built a simulator, a game, where you generate a new level. So this is kind of like Super Mario. You generate a new level every time, and you have to solve it. The goal is to get the coin in the end. If you train an agent in 500 randomly generated levels for as long as it wants to, that doesn't matter. As many training iterations as it needs to. That's not the point of this experiment. And we'll eventually get good at these 500. These are the top lines you see, the ones at the top. There are two kind of groups. You know, over the number of time steps, it gets better and better at these 500 levels. But if you then evaluate it on levels it hasn't seen, it's going to do quite poorly. Now imagine I'll let you play 500 different variants of this game. So the levels look different, you know, the walls are at different places. I think you'd be just as good as the ones you haven't seen, you know, at the ones you haven't seen, as you are at the ones you have seen. But AI today clearly is not. That's just sort of showing us the state of the art in generality. What we need to do is we need to be able to train on a low number such as 10 levels and get the same performance on evaluation as we get on training. Currently, we train on 500 and the performance on evaluation is much poorer. So we need to clearly work on the generality of the way that we train neural networks or generally AI. And okay, so how? Geoffrey Hinton, one of the people that's behind all of the algorithms that drove AI success recently, he believed in it before anyone else did. You know, he was laughed away from many opportunities just because he was interested in neural networks and backpropagation. You know what he says today? We should throw it away and start all over again. That's the guy that defended it for tens of years of his career and waited until the time came. He says it's time to throw it away. And if that guy says it, I mean, it's time to throw it away. And it's time to start thinking about better ways of training neural networks, ways that result in more generality, in better sample efficiency, and, you know, it's okay. That's what I like to say about science. We are potentially at Newton. We just discovered something that works, and that's great. Science is not about getting it right the first time. Science is about asking the question, this might be possible. This could be a solution. Let's see. And then trying it, seeing what it looks like, seeing if it works, and if it works, that's great. If it doesn't, we might need to change something. We might need to start all over again. Depends on what this is about. And we might just be at Newton currently with deep learning. We've had a lot of researchers look into this for a couple of years now. It's been going great. Deep learning is making great advances, but there just seem to be some fundamental issues. Deep learning might be a part of the solution, but it's not the end solution. At least until now, it seems like it's not. We might need to incorporate some completely new things we haven't thought about yet. As Geoffrey Hinton said, some smart PhD student, you know, he hopes that someone like that comes up with it. Maybe it's something we already know. Maybe we just need to combine things. Or maybe it is true. Maybe it isn't possible without increasing compute by even more and making neural networks even bigger. But as of today, scale hasn't helped us, at least not in achieving general intelligence. Before I end my talk, I would like to say if you want to continue this journey of exploring intelligence and learning about things and generally in developing the world, we need to keep the world alive. And currently we have some big issues on our planet, mostly climate change related. And I would strongly encourage you that if you see yourself having a future and your children having a future in 40 years' time, think about what you can do. You're the people in powerful positions, even if you think you aren't. What should a 12-year-old somewhere in Somalia do against climate change? It's us. It's us who have to do it. And there's no way to run away from it. It's going to come at us either now or much worse later. So, yeah, please do your best, whatever you can do, to take care of climate change. I'm open for a Q&A now. Sorry, I only have 3 minutes left. But, yeah, shoot it at me, please. Thanks.
Thank you, Eric, for the brilliant, brilliant talk. While we're switching to the Slido, can you tell us a bit more about what you're doing at Climate Science?
Yes, sure. We started out 4 months ago when I personally, so I come from an AI research background, obviously. I kind of realized that this is a big problem. I want to take care of it, climate change, that is. And I looked for scientific information on climate change online. And turns out you have the choice between reading biased news articles or reading research papers. I personally like research papers, being a scientist, but not everyone does. And I quickly realized that we need a fix for this, because people think, for example, nuclear is bad. Well, if you look at the numbers, nuclear turns out to be a really good solution. And there are various things like that people fight for the wrong things. That's why we started Climate Science. We want people to be able to actually act on their values and choose careers that are super impactful. Solutions are comparably close. People just don't know about them. And yeah, we gained around 60,000 followers on Instagram in just 4 months, just publishing 1 post per day, scientifically with citations about climate change and the science related to it, especially the solutions. We're now building an app for schools so that kids can learn about this in the classrooms. Clearly with Fridays for Future and all these protests, kids go to their teachers and ask them to learn about it. Turns out teachers just end up Googling things, which isn't that great. So we want to fix that.
Perfect, brilliant. So if you're not following that,
Thanks.
Another round of applause. Please follow it now. And let's dig into the questions.
Very good question.
What are possible alternatives to backpropagation,
I hope for this one.
programming?
Genetic programming, and I hope I can go over a little bit.
Please.
Genetic programming is, or genetic algorithms, genetic optimization, call it however. I'm just going to explain briefly for those that don't know. Basically, changing things randomly and hoping that it's better. So you might change some neural network weights, plus or minus, subtract, add a little bit, and hope that it performs better on your data set. It's funny, but it turns out genetic algorithms aren't that much less efficient than backpropagation on many of the deep learning tasks, especially if you parallelize them. Another interesting paper by OpenAI on that. It's pretty embarrassing for the field, to be honest, that random changes turn out to be not that much worse than our very well thought through backpropagation algorithm. But hey, no, in terms of using them as an alternative, it's still optimizing accuracy or whatever metric you want to optimize on one data set that's restricted. I would like to see an alternative, and I don't have one. I would like to see one that intrinsically wants to abstract and simplify so much that it has to learn high-level concepts, which, think about convolutional neural networks, if for those that know them, for images. They do that. They learn low-level features like edges and dots, and then from that they combine them, and they combine those, and they combine those. That's the start of that. That's the kind of that's the kind of structure I would like to see, not just in the neural network architectures, but also in the optimization we use. Force our AIs to understand and abstract over things, rather than just maximizing one metric that's not necessarily forcing that. But I don't have a clear solution, unfortunately.
Perfect. But we'll find it out very soon.
Hopefully.
Yes. So next question. I think, we're running out of time, but this is the last session anyway. Is everybody okay with taking a few more questions? Yeah? Okay, great. So next question. Is a truly general AI possible without introducing causation as proposed by Julia Pearl in the book of Why?
I haven't read the book, so I can't really answer the quote, but if the person who asked it is happy to rephrase the question so that I can answer it, go ahead.
Perfect. Then should we jump to the next question?
I mean, yeah. I'm not sure. It depends so much on the definition of general AI, and I don't want to go on for 5 minutes about that. But The way I would say, way I would define general AI, yes. What I mean by that is I can train it on 5 completely different tasks, and it, then works on a 6th task that's very similar, and it learned from all the 5 tasks to improve on the 6th. That's kind of, and it does well on it, obviously, with respectable amounts of data and compute. It's a very wishy-washy definition, so not clear how I would answer this, to be honest.
Then you guys can discuss later on.
Yes.
Yeah, continuously.
What do you think about the potential of semantic? Yes.
Which question would you like to answer? This one?
I'll answer all of them if you want me to.
Okay.
Yes, I think the next logical step, but that's sort of my personal opinion, and I should say nothing of what I'm saying is from any institution I was or am involved with. Personally, I believe that if we can manage to connect symbolic reasoning with I like to call it intuitive sense of deep learning, which is just, you give it an input, it gives you an output, it doesn't explain anything. If we can combine these things, because they both have their powers, but on their own they have huge flaws, that would be strong. And that is something I am currently working on with the same guy that did this. I drew this blob at the bottom that solved 6-player poker. That's the very sort of, you would say, not historic, what we used to do approach, and conventional approach, and not deep learning approach. I think if we can combine these two, if we find ways to have reasoning using the function approximation of neural networks, that will vastly outperform anything we have today. There are there's potential for knowledge graphs to be involved in that in one form or another, as whether that's how it's been done now or not is an open question, might be. Yeah, definitely a lot to explore in that direction. I hope this is where the field will go.
Super interesting. Okay, let's choose 2 more questions.
Yes.
Go ahead, which one would you like?
Practically, are you a Dota lover? No, I played League of Legends for a while, but I had to stop because I have too much work. Practically, what are you proposing to do
and mean by scaling thinking?
Sorry, I didn't go into this enough. When we say I should compare it to scaling data and compute. Scaling data and compute means we take the same model and the same problem, and we just throw more data and more compute at it, and then it's better. This is what we've been doing, and we've changed some algorithm stuff. But just yesterday, I read a paper. I don't know if you're familiar with the conflict between transformer neural nets and LSTM neural nets. Yesterday, I read a paper that, well, if you do this to an LSTM, it's actually better than a transformer again, which for a year, we've wasted our time just looking at transformers and saying LSTMs are shit. Sorry. But basically, instead of just looking at if we throw more compute and more data at this, it gets better. How can we go in and say, we're going to introduce a cap. I have this much budget for data, and that should be very low. I have this much budget for compute, which I think is okay to keep generous, but we shouldn't rely on it scaling up. What is the best way to solve the problem? So at that point, we cannot scale data, and we cannot scale compute. The only thing to do is make the algorithms better. If that is our only trajectory, and we define problems by how well does it do on this if I trained on that, and I don't care how well it does on that. If we defined the problems the research community is mostly involved in on these 2 principles, I think we'll move much faster towards an actually intelligent machine learning algorithm than we're currently doing. But of course, there are a million startups and big companies that make money off the way that machine learning is done today, and money comes from there, so that's what's happening. But there are groups working on the interesting parts too. Or everything's interesting, but future relevant ones.
Very, very interesting. Okay, last question.
Cool.
Let's take the top one.
Already doing transferable learning from chess to Go.
Wasn't AlphaZero already doing transferable learning from chess to shogi and finally Go? Like, exactly what are you talking about we should accomplish?
Good point. AlphaZero and many other reinforcement learning algorithms are algorithms that you can train on many games. That is, I can train it only on chess and then it plays chess. I can train it only on Go and then it plays Go. That is true for many, many algorithms. Not just AlphaZero. That's, just they gave it a name, but there is much more under the name, like the engine behind it. That's not what I mean by general AI. There are algorithms we can throw into any problem and then it does that problem. What we need is one that's trained on chess and shogi and then plays Go. And that has not been accomplished. Absolutely not. That's like the 500 game variant example I showed you, right? Even if it's the same game but slightly permuted, it doesn't work. It doesn't work properly, at least. So what should we accomplish? We should accomplish that. We should, like we do, think about it. If you learn JavaScript and Java and C# and whatever else you want, and then you're suddenly asked to pick up a new language, recently popular Dart and Flutter for mobile development, it'll take you no time because you learned the other things. Well, AI would somewhat have to start from scratch. And I would like AI to learn Dart and Flutter quicker if it already knows Java, JavaScript, and other things.
That would be super cool.
Yes.
And that makes total sense. So thank you again, Eric. And I'm sure a lot of you have still a lot of questions left.